Hello. In this video, I hope to convince you that we have the ability to predict which proton is the most acidic. And I'm going to use salicylic acid as an example. If I'm looking for the most acidic proton, what we really should be looking at is the stability of the conjugate base. That is a very common technique. Take a look at the acid. But to know the acidity of the acid, we're going to also look at the conjugate base. Now, if I think the top proton is more acidic, I would draw this anion. If I think this proton with the green arrow is more acidic, I would draw this anion. So we have two possibilities for our conjugate base. Whichever conjugate base is more stable, that will tell me which proton is most acidic. The way to determine which conjugate base is most stable, especially if they're both anions, is to use your trends. I teach SERHI, SERHI. Other professors teach ARIO, atom resonance induction orbitals. But I like SERHI, which is size, electronegativity, resonance, hybridization, induction. Those are the properties that I look at to determine who is the more stable conjugate base. Now, we don't use size or electronegativity because the negative charge is on the same atom, so there is no difference in size or electronegativity. R stands for resonance, and yeah, we have resonance for both of them, actually. Typically, I want to move this charge because I want to draw lone pairs. Oxygen that's singly bonded has 3 lone pairs. The first resonance structure that I would draw is a result of these 2 arrows. The resulting resonance structure, and I think this is the only one of relevance, is this anion here. Single bonded, double bond on the right, negative charge there, OH still there. This tells me that the negative charge, when initially here, when initially here, can actually be shared between 2 oxygens, this oxygen and this oxygen. And in real life, yes, these 2 oxygens do not have a full negative charge by themselves. They have partial negative charges because the negative charge is shared. There's only 2 resonance structures here, but they are shared between oxygens, which are very electronegative atoms. Let us take a look at our other option, where the conjugate base is on this oxygen. Now, is there a big difference here? Well, let's see what kind of resonance structures we can get. Before I move on, I might have said this already, we have a total of 2. Let me write that down. We have in orange, we have a total of 2 resonance structures or contributors. And the negative charge is shared between 2 electronegative oxygen atoms. Okay, let's take a look at our other conjugate base. The first resonance that I would draw is this. Those are my arrows. And let me draw it down. Let's go to the left a little bit. Okay, my next resonance structure, I consider this the second, is this. Negative charge here Everything else stays the same, and I will abbreviate the carboxyl group like that. Moving on, we take that lone pair and we just go systematically make the double bond, push these 2 pi electrons onto that carbon, and I have this. Double bond, negative. This is a 3rd resonance structure. And then I'm going to do one more. There. The negative charge on the carbon at the 12 o'clock position. 4 resonance structures that I am able to show. This is the negative carbon, or the carbanion. And we have that. My conclusion here is that we have 4, what color do I want to use? We have 4 resonance contributors. But what's important here is that the negative charge is shared with only 1 oxygen and 3 carbons. C, C, C. This comes from experience, but the one that's more stable is this one. It's because it's shared, the negative charge is shared between 2 oxygens. That overrides the fact that there are 4 resonance structures for this conjugate base, because it's all shared between oxygen and these 3 carbons, but carbons are not very electronegative. Right? Oxygen is very electronegative, so the charge is much more accommodated on oxygen. Very we don't get, in this case, a lot of benefit from sharing the charge with the C, because the carbons are not very electronegative. So there's little benefit in having resonances where we have it on the C. Not much stabilization. Okay. Now, I know that's kind of, for some of you, oh, he's just saying that because he knows the answer. Partly yes. I know the answer is definitely this is the better conjugate base, the more stable. But this is a very good reasoning that the negative charge is shared between only very electronegative atoms, and we have 2 oxygens. Now, so that's the answer. The more acidic proton is the one on the carboxyl group. And so I'm looking at this picture, and when we look up the pKa's, my pKa table tells me carboxylic acids have a pKa equal to 5, whereas the phenol, we call this part phenol or phenol. It's an alcohol, but it is partly stabilized by the resonance. So it's not the normal 15.5, it drops to 10. Even though it drops to 10, it's still not more acidic than this hydrogen here. The answer again to this question is this is the more acidic proton. A good explanation is not because the pKa table tells me so. When you answer why, you have to draw the resonance structures and do the analysis.